So today I'm going to be telling you today about some of the, as Mike said, some of the motivations for my work. So I study the strong nuclear force, or quantum chromodynamics is the theory of this. I'm a pencil and paper theorist. I'm one of those people you might see in the Big Bang Theory just writing on a chalkboard. That's the type of work I do. But everything I do is grounded in experiments, things we can actually observe, things we can actually learn about the world. And it's pretty exciting that the work I'm doing, we're going to have a big new machine within the next decade that's going to probe a lot of what we're trying to think about and what my work is focused on. So here in the middle, it's just a schematic of an electron up here colliding into an ion. And you can't really see it in this picture. We'll have a lot better figures later, but there are little quarks and gluons sitting inside this ion. So what we're really after is probing the substructure of matter, these quarks and gluons, how they behave, what's really going on inside the ion. And I'm going to tell you a little bit today about how we do that and try to introduce it. I can get slides moving. All right, so the Electron-Ion Collider, of course, in the title of this talk, it's this big, huge thing that we're going to be building here on American soil within the next decade. It's going to be located at Brookhaven National Laboratory on Long Island. And this, just to give you a sense of scale, this is 2.5 miles long, this big loop. So this is a gigantic machine. And it's really exciting because it's really going to be the first in the world that's doing these polarized electron and ion collisions. And ion is just a fancy word for an atom with electric charge, but really these electron and atom collisions, it's going to be the first machine of its type in the world. And we're going to get a lot of really exciting new information about what's going on with matter. Okay, so what is a collision? What do we do here? So you've probably heard of other colliders. If you watched movies like Angels and Demons, you've probably heard of CERN out in Switzerland. That's the biggest collider in the world. And it collides protons and protons, or ions and ions. In a particle collision, what happens? We slam two particles that are moving near to the speed of light together, and out comes this massive spray of new particles. And you can ask, okay, what do we do with that? How is that useful? And that's what we're going to be exploring in this talk. But effectively, sort of the elevator pitch for it is we trace back from all these particles that are coming out, these yellow and green lines. And we look at their properties. We can measure what particles they are, what's their momentum they carry, their energy, what's their mass. And we can trace back from what's happening here to what are the initial properties of these beams, what's the substructure of these particles. And we can also learn about how these things collide with each other, how they break apart and fragment into these other types of particles. What are sort of the fundamental forces of nature and how do they work? So the machine itself, as I said, it's this big 2.5 mile long loop. You've got electrons going around in one direction and atoms going around in the other direction, and we collide them at these interaction points. These things over here are just the things that sort of speed up the electrons and the ions to close to the speed of light. Just to say the speed of light, it's about 200,000 miles per second. So these things are going extremely fast around, maybe like 100,000 times in a second around this loop. So very, very fast, very energetic, very exciting. And to do this, it's about a $3 billion investment. To build these things, they're capitalizing on the one existing collider in the US right now called the Relativistic Heavy Ion Collider, building on some of the machinery there. But this project, to even get it to this point, it's been decades in the making. People have been talking about building an electron-ion collider since the early 1990s. And it's been a lot of planning and exciting development since. And it's going to take about a decade to build. Right here, this is one of the existing tunnels at Brookhaven where these ion collisions are happening right now. Just to give you a sense of scale and what this looks like. These are huge tunnels. And in particular for the EIC, this is sort of a schematic of what we think those tunnels are going to look like. This is, you can tell, 3 stories tall where these detectors are, where we're going to be making these collisions and slamming things together and measuring these particles. It's like, this is about 30 feet long and 20 feet tall. So these things are huge. The particle sprays they create are huge. And it's very exciting. They're also going to have detectors far away to catch particles that travel really far. Well, one of these things looks like, this is currently the STAR detector at Brookhaven, which is again measuring ion-ion collisions, which are probing something called quark-gluon plasma, a completely different phase of matter than we're used to. But the EIC is going to be probing, the things around us that we're using, the type of matter like protons and ions that we see every day. Okay, so who's building the EIC? This is just sort of an introduction. I'm trying to give you a flavor for what we're doing before we get into the science. Of course, all science in the US, all the basic research, basic physics research is usually happening in one of two places. A university like here or at one of the national labs. If you've seen Oppenheimer, that's like Los Alamos National Lab. That's my employer right now. Here's the main gate, the old main gate. You can go up to it. It's actually outside the lab right now. So you might be surprised if you're not as familiar with what's going on. University professors are not just people teaching the college students, standing up at the board every day. They also train a lot of our scientific workforce who are doing this basic research. And sort of the path is you do a PhD, which lasts 5 or 6 years after your undergraduate degree. Then you do training for 3 to 6 years as a postdoc. That's the stage I'm at right now. And then you go on to lead your own research group at a national lab or as a professor. So the national labs, there are actually 17 of them, I think. So Los Alamos in New Mexico, that's where I work. The EIC site in Brookhaven, that's on Long Island. And then there are a lot of other places. There's Jefferson Lab in Virginia, where there's a fixed target experiment. There's Argonne and Fermi Lab up in Chicago, which are nearby, and then all sorts of other places. And of course, other agencies have labs. Los Alamos is actually partially run by the National Nuclear Security Administration, of course. Lots of nuclear bomb stuff happens at Los Alamos. In Missouri, we also have an NNSA facility out in Kansas City. You know, there's also Department of Defense labs, NASA labs, all sorts of stuff all over. And this is where basic research is happening. Okay, so now that I've given you sort of an introduction, what is it, who's doing it, let's get into the science and figure out why are we building this EIC? What's going to happen with it? What are we going to learn? What are we expecting to get out of it? Then we're going to talk about the inner structure of matter. We'll actually go from this bird's eye view here to actually going into depth. What is the matter around you made out of? What do we know? What don't we know? What are we expecting to learn? And then after that, we're going to talk about what is the EIC going to buy us? What exciting new things are we going to expect to learn in the next few decades? So if you have any questions, feel free to stop me. I'm happy to answer them about anything. If you have any questions now, before I move on, anybody?
Oh, yeah, a quick question.
Yeah.
Are you being affected by these funding cuts?
I have not been affected by the funding cuts. I think Los Alamos, I think there were some funding cuts, but they were small there. There are other places around that have obviously been hugely affected. I think WashU has a lot of NIH funding, but so far not Los Alamos.
Are there, other than Brookhaven, are there any existing collider facilities in the United States?
There are none that are running right now except for the Ion Collider at Brookhaven. I think the previous one was the Tevatron up in Chicago, which turned off in 2010s.
That's the one I was thinking about.
Yeah.
You mentioned,
Oh, go ahead.
you mentioned charged atoms. Does it make a big difference if they're charged versus not charged?
So the way that we actually accelerate things at accelerators, we sort of hit things with an electric field, and that's how we get them going, an electric force. So you really do need a charging particle, and that's the easiest way to provide things.
So in your title, you use the term strong force. If you're going to define that for us, then I'll shut up.
I'm going to define it for you, but I can give you a hint to things. So there are 4 forces in nature. Of course, gravity, that's what makes things fall. Sorry, Mike, your laser. There's the electromagnetic force. So, you know, picture a lightning strike. That's what that is. And then there are 2 forces that you can't really see in your everyday life that are holding nuclei together and mediating a lot of those interactions of smaller particles. And we'll go into this in a lot more depth later, but these are called the weak and the strong nuclear force. And I'll talk about this later in my talk and what exactly they do, what particles they talk to, and how they make up matter.
And the particles scatters when they collide. You need a 3-story by 3-story by 3-story volume to detect all of that?
Yeah, we're not even picking up everything. There are only certain particles, there are only a small amount you can pick up. So like protons and electrons and photons, things we're familiar with, ions and kaons. But there are like hundreds of other particles out there we can't even detect because they either disappear too fast or, you know, things are just scattered all over the place. So yes, we do need these huge detectors. And the fundamental reason is that, first of all, these are very complicated collisions, but also they're happening really close to the speed of light. It's a ton of energy. So you can form a ton of matter.
I think pivoting off his question, what is the cross section of the collisions? Is it in meters or is it in centimeters?
I mean, so how you want to think about these particles, they're like microscopic. So a proton is a femtometer wide. So you're hitting just teeny tiny things together and they're coming in particle bunches. So it's really microscopic, but it creates this huge amount of stuff coming out. Anybody before I move on? Oh, yes.
I have a quick one. So when you build the EIC, are you leveraging anything other than the site? Are you leveraging the tunnel? I mean, is it a
Yeah, so-
completely new, like?
So these ion rings are already there. They're gonna have to build an electron ring, but it's basically, a lot of it's already happening in the tunnel. There was actually there were sort of two proposals put up to the DOE for building the EIC, and one of them was to build it at Brookhaven, and the other one was to capitalize on existing stuff at Jefferson Lab. There's a machine called CBAF there, and they decided on Brookhaven because there was so much existing stuff there. And so like the detectors are gonna have to be entirely new, this electron ring is gonna have to be entirely new, there are gonna be upgrades. But there's a lot of stuff already there. We're also capitalizing on the existing knowledge in the United States and beyond. Really, we have some of the most talented nuclear particle physicists in the world, talented experimentalists who already are working on these detectors, working on the technology, and figuring out what we need to do. So it's both, we're leveraging human capital and some of the existing stuff.
And just to scale it, it's 2.5 mile circumference.
Yeah,
And CERN is like 20 something miles.
it's like 20 something miles. This one you can actually drive around. I remember the first time I visited Brookhaven, one of the theoretical physicists I was talking to said he didn't know how to drive until he came there. And of course, Long Island, you can't get around by car. And he said that one of the other physicists taught him to drive by just driving around on the road on top of this collider in circles until he figured it out. Yes.
So if you're circulating these particles, is it your idea to have two opposing circular beams to impact each other?
Yeah, because you get a lot more energy if you're colliding two things coming to each other than just running into a straight wall.
So if those have to be aligned, aligning a particle beam that's that small with another one that's that small going in opposite direction would seem to be just a gargantuan task.
It is a gargantuan task, but people have figured out how to do this, and that's something that's completely amazing.
And are they able to calculate the degree of angle if they're off, because obviously that calculations would be way different.
Yeah, they have calibrations for all of this, and it's extremely impressive. And they actually use magnets to focus these things all along the way, because you have to keep these beams going in the circle the whole way along as you're sending these beams around in the circle.
Are you gonna talk more about that today?
I'm not gonna talk as much about the experimentation because I'm not somebody who works on this, but maybe you can talk Mike into inviting somebody here one day who actually is hands-on building these things.
Thank you.
Just one more quick question. You mentioned, obviously 2 ions are colliding. Literally 2 ions. But when you accelerate the stuff, it's more than just 2. There's a cloud.
Yeah, there's a cloud of them, but because these things are so small, you have to send a whole bunch together to even get one collision.
So there's a whole bunch of collisions and then there's a whole bunch of particles that can come out.
So, and they're able to trace back, did one collision happen and stuff's coming out, did multiple happen? Their effects pile up where you get just a bunch of stuff happening that can contaminate data. But people know how to handle this and analyze all of this. So, and there's, to give you a sense of scale, there are thousands of people who work on collider physics just for even a single collider, thinking about all the theory and the experimental facets of this. You can have people spending an entire PhD just focused on, a single part of a single detector, or spending their entire career on that. It's really amazing. All right, but there's so much more that can be said about this. People will spend entire semesters, entire years doing courses teaching people about this. And we only have an hour. So I'm gonna move on and just do a quick why the EIC. Okay, so the scientific motivation, as I've already sort of alluded to, this is an artist's depiction of what the inside of a proton looks like. If you look around you, every single thing around you is made out of molecules, and molecules are made out of protons. This is one of the most popular widespread particles in our universe, and it's this gigantic mess, and we don't know everything about it, which is kind of shocking. And we're already in 2025. So one of the big motivations is figuring out what's going on inside protons and atoms. Beyond that, there are also broader impacts. As I've alluded to, the US has some of the top nuclear and particle physicists in the world. And by building these things, these 10-year building periods, having people like me working on the theoretical physics, that's training our workforce, developing a workforce that's skilled in nuclear and particle physics, which have really big impacts. I'm going to just go through this fairly quickly. But what are some of the sort of indirect impacts that we expect? Of course, we're building accelerators, improving the sort of accelerator technology we have around, which I've taken it from the EIC science overview, but accelerators are used in microelectronics, therapeutic drugs, batteries, and more. They can impact the development of those. In health and medicine, of course, isotope production, high-resolution PET scans, if you've ever had a PET scan for anything that's really based on the underlying physics. Developing advanced technologies could lead to more particle beam approaches for diagnosing and treating cancer. Energy and national security, of course, once you say nuclear physics, we all know what that makes you think of. But also even things like scanning and screening cargo at ports of entry. People are, of course, developing a lot of AI and computational tools in the context of developing these particle accelerators. So often there are fundamental advances in even computational tools. And of course, the EIC, we're spending $3 billion to build something at Brookhaven. So of course, it's going to make a major economic impact. And then also beyond that, what is basic research good for? We're just trying to figure out what's inside a proton, right? How could that be good for anything? Well, CERN, the big collider over in Switzerland and France, that was actually where the World Wide Web was developed. They were trying to figure out how do we send all this particle data to various universities and where people are developing things. Well, actually, the World Wide Web was developed to do that. And now, because of that, you can check the news online or watch YouTube videos or whatever, and that's all the consequence of particle physicists sitting around thinking about their data. Of course, then you could ask about something more esoteric, where you're not actually developing something. What about quantum mechanics? That's just this awkward theory about small particles, right? Well, your smartphone depends on that. Lasers depend on that. MRI, GPS, you even finding your way here when driving. That all depends on quantum mechanics, and that has all come as an outgrowth of this fundamental basic physics research. Then, of course, as I said, medical applications and national security are two outcomes of particle accelerators, two applications of these. So basic research really lays the foundation for technological innovation. You can't develop new technologies unless you have new materials and new ideas to work with. And then, of course, the final thing people often say about this is we're developing, of course, our workforce here in the US, and we're bringing really great talent from all over the world to work on this Electron-Ion Collider. So it's an exciting time, and there are a lot of impacts just beyond just finding these basic facts out about the world. And there are potential impacts. You never really know when you're doing fundamental physics what somebody's going to do with it practically 50 years from now. Nobody who worked on quantum mechanics and who was trying to think, how are these little particles bouncing around? Nobody thought it would lead to Angry Birds on your phone or watching Taylor Swift videos on your phone. But, that's what we get from it. So. And a lot more useful stuff too. Okay. Are we all on board with why do we build these things? Why do we do basic research? Why do we care about physics? Good? Questions, thoughts, concerns? All right. So now we get to why we're here, and that's to teach you about the inner structure of matter. What the world is made out of, what's going on with these protons. So I know, I have physicists like Mike in the audience who have been thinking about this all their life. My mom and dad are in the back, and I know they haven't thought about this at all. So I'm really going to start at the beginning. I hope you guys aren't insulted. I'm going to go slowly at first, but I want everybody to be on the same page. If my dad starts falling asleep, I'll know that I have not done it slowly enough. It's okay if you do, Dad. Okay. So substances, you look around you, you look at my water over here, they're made out of molecules. So water, it's just one thing, one substance, it's just water molecules. Other things can be made out of multiple substances. I had coffee this morning, I had milk in it, I had sugar in it, there's of course caffeine in it, and all of these are separate individual constituents, basic constituents of these things. This table is made out of wood or some fake wood, and it's got molecules in it, pewter, chalkboard. Basic substances. What does a molecule look like? Well, molecules can be broken down into individual atoms. So water, of course, you've heard is H2O. It's just an oxygen sharing some electrons with some hydrogen. And they sort of stick together, and that's it. Every single water molecule you'll see, they all look exactly the same. They're these little building blocks. Same thing with caffeine. It's a little bit more complicated. These vertices here that are unlabeled are carbon, and if it's sticking out, it's got a hydrogen at the end. People don't typically label these. But again, it's just some carbon, oxygen, nitrogen, and hydrogen connected in some very specific way. And no matter what caffeine molecule you look at, they're all gonna just be comprised of the same set of atoms in the same order, in the same configuration. Of course, you can get a lot more complicated than this. Proteins and things can have thousands of atoms in them, thousands of little pieces, but these are two basic ones that we encounter every day. Okay, so now that we know what's in our water and our coffee, let's go a little further. What is this hydrogen? Is it something basic or is there more to it? What about the oxygen? Well, as you know, science got better and better. Once people figured out about molecules, once people figured out about atoms, they started looking inside the atom and asked, can we break it down into even more fundamental pieces? And what they found out is, okay, there's a bunch of protons and neutrons sitting together in this core nucleus, and then there are a bunch of electrons just circling around them. And every atom is characterized by how many neutrons and protons are sitting inside of it. And so hydrogen has just one little proton in there, oxygen has 18 of them, and same with any other atom you pick out. So we can classify these, and now we know what's happening with them. Can we go even smaller? Well, protons are made out of quarks and gluons. And this is where we get to the strong force. Somebody had a question earlier. And this is just a schematic depiction. As I said, we don't have a full picture of what's inside the proton. So, you know, with water, we can take it, we can look under a microscope or whatever, we can take various substances and figure out what they're made out of. We can pull them apart, we can pull out an individual oxygen atom or something and look at it, and we can figure out what it's made out of. But protons are a little bit more complicated. So at the energy we have here on Earth, at the pressures and temperatures that we experience and that we can make up, you can't actually pull an individual quark outside a proton and look at it. The force that binds these quarks and gluons together, it's called the strong force. It's so strong that if I tried to pull two quarks apart so that I could look at one of them, it's so strong, there's so much energy used in that process that as I pull them apart, eventually I pull them far enough that a new quark-anti-quark pair forms in the middle. You get new quarks coming about. You can't actually pull something out, the force is too strong. I mean, that's not 100% of everything. There are places where you can get quarks and gluons that are not bound inside protons, but I mean, these circumstances are like the first millionth of a second after the Big Bang, or the inner core of a neutron star, which packs the mass of our sun into a ball the size of Manhattan. So you have to have really extreme pressures, really extreme temperatures to get the quarks or the gluons not to be confined inside protons. So that makes it really hard to figure out, you know, what's going on inside of these. We can't see them individually. We can't really see inside the proton. So we have to really find out what's going on indirectly. So what are quarks and gluons? Those aren't the only things out there, but they are all that we'll talk about today. If we look at the types of matter that we know about so far, we can divide them into two things. There are the particles and there are the force carriers. So particles are divided into quarks and leptons. Leptons are things like the electrons and their cousins, muons and taus, which are like heavier electrons. And then there are really elusive particles called neutrinos that are really light. Quarks, there are 6 types of them: up, down, strange, charm, bottom, and top. No, I don't know who named them or why they named them that way, but that's what we have and we're stuck with. And then the interactions between these guys are mediated by things called bosons, the Higgs boson, the God particle you've probably heard of in the news that was just discovered about a decade ago. The photon, you know, that's just light. And then there are other particles called W and Z bosons, which mediate that weak force. Photons mediate electromagnetism, gluons mediate the strong force, and then there are also hypothesized gravitons that are responsible for gravity. So this is just a chart, you don't have to remember it, just have to remember the strong force we're gonna talk about today, everything going on inside the proton, it's quarks over here and gluons over there. Yes.
Would it ever be possible to accelerate quarks or gluons, or is that too much energy? You can never build a collider that would provide the then give you different information about subatomic particles.
So to get an isolated quark or gluon that we could accelerate, you'd have to get those extreme temperatures and pressures. We do know how to form, so the substance that these form when they're not inside a proton at those extreme temperatures and pressures, it's called quark-gluon plasma. And we can form it at the existing collider, the collider that's shutting down this year at Brookhaven. So we can build the EIC, it's called the Relativistic Heavy Ion Collider, or RHIC. So they can actually form this quark-gluon plasma, but the longest we can make it last is something like 10 to the minus 24 seconds. So that's a millionth of a millionth of a millionth of a millionth, or something like this. So very, very small amounts of time. So we don't have the technology yet. We don't have the ability yet. I don't know if we ever will, to be able to really play around with quarks and gluons like that. But by slamming different particles together, so at this electron-ion collider, we can slam electrons and protons together. We can slam electrons and gold atoms together, electrons and lead. We can probe different properties by doing that. But really our tools, they're very indirect and we have a very limited amount of tools. So people like Mike and I, we try to think of clever ways of finding out new information from these and really maximizing on the data we have. And then we can lay out what sort of collider we want in the future and what we'd ideally want, but we can't arbitrarily pick out particles to collide just because these are billion-dollar projects and the technology is limited. But it's exciting how far we've come.
Is this ever going to come to a place where you can define dark matter? Are these collisions going to give you any information about what that is?
Yeah, so dark matter, people have proposed various things it might be or various signals we might see. People have said that there are some signals that might potentially be observable at the electron collider of dark matter that might pick out specific types of it. But we don't know if it is that type of dark matter. We don't know if the signals would be strong enough. We don't know if we'll see it. But certainly, I have a lot of friends who work on dark matter and are trying to come up with what could we see at a collider that would help us find out about this. So that's an ongoing question, and there are many ways. Astrophysicists are looking for dark matter, collider physicists are working for dark matter, mini probes, but because we don't have any clue what it's going to look like, we don't have a definitive, this experiment will discover it. But it'll be exciting when it is discovered. Yes.
Is there any possibility that just by happy chance you could develop a micro black hole?
I mean, I think people were worried about this when CERN turned on and nothing happened. This is going to be a lower energy than CERN. So I don't think that's really concerned with collider physics, but good question. Thank you.
I would suggest that you repeat the question when you hear it before you answer it. Many of us are not in a position, and the speaker who asks the question doesn't have a mic.
That's a good point. I didn't think of that, sorry. But the most recent question was about micro black holes and whether we're worried if one will form, but we are not worried. And remind me in the future if I forget with the next question, and I will. Thank you. Yes.
Go back to the chart.
Yes.
I was just going to ask about the TBD over there. Do we know there's another particle out there, or
So
is it just a placeholder because
it's a placeholder because we don't know what it is, but we have a lot of evidence that it should be there. Oh, yeah. Oh, yes, repeat. So do we know what dark matter will be? Do we know what the TBD is? Do we know if there is even a TBD? So if you look out in outer space, you can look at how all these objects out there, galaxies, stars, all of these things, how they're moving. And of course, the force of gravity is the dominant thing telling you how things are moving out there. And the way things are moving tells us there should be a lot of mass out there, and we can figure out how much mass there should be that's causing this gravitation. We can also sort of look at the light coming from these things, the types of light, the amount of light, and also estimate the amount of mass that way. And of course, we have lots of other probes. But our expectations for what there is based on different things, they don't match up. And it tells us there's some missing mass. It's dark. We don't see it. We don't see light coming from it. And there has to be something there, but nothing else on this chart could possibly explain it. And we don't think dark matter, it might not even interact at all with anything else in this chart. So figuring out what's going on there, what's causing this gravitational force, where is this mass coming from is the question of what is dark matter.
You know, it's not quarks and leptons.
We know it's not quarks and leptons.
Do you think you found all the flavors of neutrinos because they changed from one to the other, but they think there may be a fourth neutrino that makes them change? Is that something you can find with the collider?
Not at this collider, but I mean, people have proposed things called like sterile neutrinos that we might not have seen before.
Repeat the question.
Oh, yes, sorry. Do we think there are other types of neutrinos? And I'm saying people have proposed them. But this collider is not searching for that particular thing. Yes.
Your chart up there divides fundamentally into two divisions, one called force carriers and one called particles. I don't understand that division because there are obviously forces under particles. I mean, electrons are charged, they carry forces. What's the division that you're making there?
Okay, so the question is, why are we dividing things into forces and particles? So you're right, the W and the Z bosons, they're particles. The gluon is a particle, the Higgs boson is a particle. But I guess the fundamental nature of the division is, so the mathematical equations describing these, and the structure of these is different than the structure of those. So we can.
Question by the gravitron, is the gravitron particle a wave or both?
We have not observed. Okay, so the question is, what's the graviton? We have not observed a graviton yet. It's thought to be out there because we know there's a force of gravity. We know that these photons and these gluons and these W and Z bosons, we can construct the mathematical equations governing all of this, and we can see how it all comes out in sort of this particle form. The graviton, we know how the force of gravity works, but we have not observed something consistent with a graviton particle. So we do not know what its properties are or what it would be, other than that we know gravity is out there. Does that make sense?
Isn't it the difference between mass and no mass? Force carriers don't have mass.
So the W and Z bosons are actually massive. They're hugely massive. So, and the gluons and the photons are massless, but the Higgs boson has mass of like 125 MeV also. So it's not a difference of mass. It's just how we conceptualize, how we make sense of these equations, and how we make sense of the forces going between these things. Usually these things are virtual, and you're not observing them. They're being exchanged between two particles to mediate this force. Does that make sense? It's hard to explain things without the equations. Mike, did you want to say something? No? Well, the equations, I can show you, they're here. So this is the entire equation describing particle physics. You can buy it from CERN on a coffee mug. So these are the gauge bosons up here. These are the force carriers are described by this top line. The quarks are described by this next line. Various fermions here, and then the Higgs field. And basically what these equations are saying, you can translate them into the different interactions and emissions particles can do. So here, if you picture time going in that direction, this part of the equation says, well, I can have a quark that splits off into a quark and a gluon. Or I can have a gluon that splits off into two gluons, or it can annihilate two gluons and they form two other gluons. So here's your equation. It was actually great timing, whoever asked this. But those force carriers are all up here. And it's very nice that everything we can see in the world around us, other than dark matter and things, can be explained with a coffee mug. And what we're talking about today, the quarks and gluons, they can be described with just three types of interactions. You can have two gluons coming together and going to a single gluon, or one going into two. You can have four gluon vertices where you have two coming in and two coming out. You can have a quark split off into a quark and gluon, or you can rotate the diagram and have a gluon going into a quark and an anti-quark. But all there are only three types of ways that these quarks and gluons can interact. And of course, the strong force is this interaction.
These are Feynman diagrams, aren't they?
Yes. Very good. They're Feynman diagrams was the question.
Quick question. You said, so these are the only type of interactions. If they don't interact, what do they do? Just kind of bounce off each other?
So I'll talk about what happens in a particle collision later, so come back to that. So why do we call it chromodynamics? So the mathematical equations describing these, well, it says there's sort of three types of charges there can be. They're nicknamed red, green, and blue. This contrasts with something like electromagnetism, where you can have a plus or a minus charge. It can be positively charged, negatively charged. Here we have three different types, and it's convenient to just call them red, green, and blue. Interestingly, all the particles we observe, like protons, all these composite particles, they have no total color. You have one red, one green, one blue, and that people would say it's like white or colorless. But chromodynamics just comes from this color charge, and it's got some interesting mathematics behind it, why we use RGB instead of plus and minus. But that's, there could be a whole course on things like this, so we're not going to do the details today. Okay. This is a problem. I'm at 40 minutes. I'm only halfway through my talk. I've got 55 slides, but just to recap what I've said so far, everything around you is molecules. This is the caffeine molecule. You look inside any one of the atoms sitting in the molecule, and you get this. You get a bunch of protons, neutrons, and electrons. Look inside a proton, and you get this huge mess. So, sort of two of the big questions in physics right now are, what's really going on inside this proton? What is this mess? How do we characterize it? And really, how does this come about? How do you get that huge mess from just these three types of interactions between particles? It's kind of amazing that this happens. And these are questions we don't have the complete answer to, but that's why physicists like me have job security, and we're building these massive colliders. The sort of the naive story that you might have heard if you've taken a basic physics class is that the proton has two up quarks, a down quark, and they're glued together by gluons. As I showed you, it's really just this sophisticated mess. Sort of the valence quarks, those two ups and one down, you can think of them as dominating the behavior, but there's also a sea of gluons bouncing around in here, and particle-antiparticle pairs can spontaneously form out of the vacuum or disappear back into it and annihilate. So that's sort of the next sort of step into looking what's happening in the proton. Why is it so complex? Good? So then the next question you can ask, how much better can we get in this description? Can I make a map of what's inside the proton? Can I make a really pretty picture like that atom and just draw that out? And I know exactly where everything should be placed and how it works and how it evolves over time. Unfortunately, we can't. So these things are at a really small scale. They're described by quantum mechanics. And there's a very important principle in quantum mechanics called the uncertainty principle that says you can never know the position and the momentum of a particle precisely at the same time. What this means for the proton is that means you can't really make a map of what's going on inside the proton. You can't say I have a quark here and the next second it's going to be over there and then over there and it's going to split off and it's going to do things. You can't do that. You can't draw a very precise picture of the proton and how it evolves and how things bounce around. The best we can do is determine a probability map. What's the probability that if I bang this proton with an electron, I'm going to see an up quark? What's the probability I see a down quark that's moving very fast? What's the probability I see something with a certain spin? You can ask questions like that, and that's how the closest we can get to a map of a proton. So these types of maps we call parton distribution functions. These were first discovered in 1969. At what was called the SLAC MIT experiment. SLAC is another one of those national labs. It's located at Stanford in California. So 1969, we got sort of the first 1D picture of how quarks and gluons are distributed inside the proton. So you can think, the question is here, what's the probability I slam an electron into a proton? And because these things are moving so fast, it effectively bounces off a quark. It interacts with a quark through a photon. And you can ask, okay, how many times do I see this process occurring at a collider? And theorists have determined that you can determine that cross-section. It's really just a coefficient, some number you can calculate by hand, times this parton distribution function, the probability of hitting this particular quark or gluon. So if I measure this thing in an experiment and I calculate this coefficient by hand, I can extract this picture of what's happening inside the proton. So X is sort of the momentum of the up or the down quark inside the proton. It's a momentum fraction, actually. So X is asking if this thing is moving with momentum P, and what's the probability I hit a quark or gluon with a fraction X of that overall momentum. And you can draw what's that probability that I hit an up quark with that momentum, how often do I hit a down quark, and you can draw nice graphs, and these you can extract from all the various experiments we have. And gluons, there are a lot of low energy gluons. We'll come back to that later. And you have this map. So we had these first maps in 1969. We're now 70 years later, and we're now still trying to generalize that picture to 3 dimensions. If I look inside the proton, what's the probability I find a quark with that longitudinal momentum? But now I also want to know, how is it wiggling up and down? How is it wiggling side to side? This thing is 3D, not just 1D. So instead of just asking about this one feature, now can I ask, can I get a full 3D picture of the momentum of the proton? And people have started to do this and to try to create maps of this. These are spatial and momentum distributions that I'm showing here. And you can start to create these pictures. And that's very exciting. So we're starting to get probability maps. You can go even further. Again, I said these 1D maps at SLAC in the 1960s. Of course, there have been other facilities since then. DAISY was a collider in Germany in the 90s. CERN, of course, we all know. Jefferson Lab is a facility in Virginia. The Electron-Ion Collider that we're building. So we've gone from 1D to 3D. We're now starting to get better pictures of the 3D, but we're going to get much better 3D maps from the EIC. You can combine spatial and momentum information into what's called a GTMD, but we're starting to get more precise maps, more detailed maps of what's going on. And we can also start asking other questions about other features of the proton too. And we're starting to do these maps. But what's really amazing here is SLAC, again, 1960s, 2030s, we're still asking these questions, still trying to find it out. It's very difficult physics, very difficult experiments to build, very sophisticated. But you know all the matter around us. Don't you wonder what's there? Yes.
Good question. That uncertainty principle, is that been proven, or is that just shows the lack of our ability to get to the level? Because, you know, if you see a ball, you know it's right there, and, you know, so it's kind of disconcerting to say, well, we really will never know where it is exactly and what its momentum is exactly.
Yeah. So the question is about the uncertainty principle. Is that something we know? So this is, I mean, quantum mechanics is extremely bizarre. It's very different from anything. It completely defies the intuition we have at the classical level in very big particles. We know the equations of quantum mechanics hold, and we know that these uncertainty principles come straight out of these equations. We know we can't access that position and momentum information. It's bizarre, it's disturbing, it bothers me, but that's what nature gave us.
How does this fit in string theory? Everything is a field of springs, ultimately of springs. How does this fit in with string theory?
So the question is, how does this fit in with string theory? So string theory, we don't actually have a complete theory yet. People don't exactly know how that connects to the standard model, but it's a theory that's been proposed, that's being developed to explain all of these forces and particles and how they come together and whether there's something even more fundamental than what we're seeing. Some more fundamental unifying principle. So string theory would have to align with what we already know about quantum mechanics, about all of these particles. But ultimately, we don't know what string theory is going to give us or tell us about these features, other than that they have string theory. If it is the fundamental theory of nature, it has to align with what we already know and explain the observations we've already made. But that's a good question. Anyone else? All right. So there's a lot we want to find out. We can also extend this. I've only talked about protons so far, what's going on with the quark or the gluon inside the proton. We can also ask this question about atoms. If you just look at this picture of an atom, these yellow and black dots are meant to represent protons or neutrons. You might think, okay, it's just a proton sitting next to a neutron and they've each got their own thing going on. So it should just behave as that. But the thing is, the whole is greater than the sum of its parts. These quarks and gluons inside individual protons and neutrons, they're sitting next to each other. We know the interactions and the strong force. Things are going on beyond just having two isolated protons and neutrons sitting together. If you look at the data, the predictions we can make for these collider processes, it's not that, an oxygen atom has 18 particles inside of it and it's just 18 times what we have. It's actually much more complicated than that. The curves are up and down from what you would expect as a flat line of a pure atom divided by a pure proton. It's not just the number of protons and neutrons inside. Yes.
So are you suggesting that if I have a proton and a neutron in close proximity, that there's an interaction across the boundary?
Yes, if they're in an atom together, effectively that level of closeness. Yes.
Have we identified all the constituent parameters that describe, or independent variables that describe the behavior of neutrons and protons and quarks?
Have we described all the independent variables do we know the independent variables that describe protons and neutrons? So this is an interesting question. So just backing up to this picture here, you could say, okay, we know all the independent variables of a molecule. A molecule is this big thing. We can see how it moves up and down, how it interacts with other things. And that's a reasonable approximation. If you didn't know about what an atom was, you could still describe a molecule pretty well. Until you start probing in really close, when you start looking really close to one of these oxygen atoms, when you get to these small scales, then the effects of the atom start to take effect and they start to become important once you're looking at the scale of the atom. And the same thing when you look at an atom, you can describe it, you can come up with some parameterization of how it's behaving fairly well if you're zoomed out far enough. But when you start zooming in and looking at the atom too closely, you get too close to a proton, all of a sudden these effects start to become relevant. So in physics, so actually the area of physics I work on is called effective field theory. And it's about trying to determine for each individual process, each individual phenomenon you want to look at, what are the most relevant degrees of freedom for the scale you want to probe it at. So if you're trying to figure out how to get, I don't know, from St. Louis to the Collider in New York, and you're looking from a satellite, you can just draw a line from the two. Now, when you zoom in and you start seeing the highways, you're going to need more detail for that. And then when you start zooming into St. Louis itself and you have to figure out how do I get on Highway 40 or whatever you're taking. I guess you take 40 up. I don't know what direction you go when you go up to Chicago and then over. I don't know. But wherever you go, you're going to need to then know where the stop signs, the stop lights inside town itself. And it's the same thing in physics. If you're looking far away, you don't need as much information as when you're looking close. So the mathematical descriptions are different. And of course, string theory is something designed to describe when you get down to those very low energy scales, what's going on. But we don't know yet because we don't have things that can probe those energy scales. Yes?
Well, back to the strong force. The example of the oxygen molecule. The strong force is working inside the proton. Is the strong force what's holding the protons and neutrons together also?
Yeah, so the strong and the weak forces come into effect. So the question was, what's holding together the proton? What's interacting with this protons and neutrons? It's the strong and the weak force come into play, holding these different particles together, describing interactions between two things sitting close to each other. The quarks and the gluons and the W and the Z bosons and all these particles come into play. Yes.
I'm excited to hear what you have to say. Please keep going with your slide. Thank you.
Sorry. Lots of interesting questions. Okay, the next thing I wanted to say, though, I showed you these nice, beautiful pictures of what's going on inside the proton at 3D. That picture is incomplete. So if you actually look at data, I'm just showing you two aspects of TMDs. It doesn't really matter what they are in detail, but you can see all these models we've made. There are huge error bands in the models we've made for different areas of parameter space. They diverge. The purple line doesn't match up with the orange, which doesn't match up with the red dots. Likewise, up here, it looks like a nice picture. What does a TMD look like? But if you look at the uncertainty bands, as you start to get farther and farther out from this plane here, you have uncertainties reaching as high as like 20% and even worse in some areas. So I can draw those nice pictures for you, but there is a lot of uncertainty on top of them, and we don't know everything there is to know. So I'm just gonna breeze through this. I only have 5 minutes. How do we research proton structure? I do analytic theory and a little bit of numerics, and so does Mike. And then you can also think about experiments and phenomenology. And phenomenology, that's a fancy word, meaning how do we extract information from an experiment? How do we get from the experimental outcome to some sort of fundamental knowledge of the phenomena in physics? Analytics, that's pen and paper, numerics, running a big computer. So analytics, again, we have this simple equation describing how particles interact. But how do we get from this thing we can fit on a coffee mug to the inner structure of a proton? That's a very complex question. If we use numerical tools, the main method is called lattice QCD. And if you ask, okay, why aren't we using numerics for everything if the analytics are so hard? Well, a single calculation, it can take months on a supercomputer that costs hundreds of millions of dollars. So numerics are good for some things, but they can't completely replace analytics. And then, of course, phenomenology, when we talk about building these colliders, they're billions of dollars to construct. They take decades to create, come up with the ideas to further the technology we need for them. And it costs billions of dollars. So the best we can do with physics is to synergize these techniques. Sometimes we can use techniques for the same thing, same tool, or different tools to answer the same question. This cross-checks that both methods are working. But oftentimes we're trying to piece together different pieces of information from numerics, analytics, and phenomenology to get our understanding of particle physics as a whole. And that's why we need an EIC. So, and again, only have a few minutes. I'm gonna breeze through this. You can ask me questions afterwards if you want to learn more. Why is the EIC exciting? Well, it's the first electron-ion collider in the entire world. This is the first time we're doing experiments like this, slamming two electron and ion beams together with polarization, with all these properties that are going to let us look inside these proton atoms. It's very highly sophisticated instrumentation. Again, remember this thing was 3 stories tall and like 100 feet wide. It's going to have a much huger energy range. So these blue and these sort of dark brown lines are data we've taken before. This yellow area drawn here is what the energy range we're going to be able to probe with the EIC. So you don't need to know the details on this chart. All you need to know is this big yellow blob is much bigger than what we already have access to. There's going to be a lot of data, very high luminosity. So there are some things you can explore with lower luminosity, but as you get to higher luminosity, there's a lot more we can access and a lot of exciting things we can explore. So that's a great thing about the EIC is we're going to get a ton more information. And then I'm going to just breeze through quickly, recap what I said, and again, ask me questions afterwards. I want to make sure everybody who has to go gets to see sort of the end of the talk. We're going to get higher precision maps of what's going on inside the proton and what's going on inside atoms. We're going to learn about the origin of proton spin and mass. Of course, you might think, okay, maybe all the spin is coming from the gluons, and some is coming from the quarks, and some is coming from these interactions, the orbital angular momentum. How much is coming from each? And the EIC is going to give us a lot more data about that. Same thing with the proton mass. How does it come about as the sum of these parts and the various things going on inside of it? The saturation frontier, this is something I personally research and think a lot about, is, okay, so we saw that chart. Do you remember the parton distribution function where I said these gluons, it goes way up? As you start looking for lower and lower energy gluons, the amount of gluons you see really increases. Well, and it looks like it's just going to keep going up. So it was applied. Let's make it clear. So the amount of gluons you see as you go to lower energy blows up. Well, you wouldn't expect that the proton becomes infinitely filled with gluons. It can't pack an infinite amount of stuff into it. You would expect at some point the amount of gluons you see saturates. These gluon parton distribution functions, they saturate. And the question is, where does this happen? How does it happen? Why does it happen? And that's something that the EIC is chasing. confinement, again, how do these three basic interactions lead to this very complicated picture? That's a very big and important open question in physics. What's going on inside atoms? So basically, everything I said on the past slide, it's not just the proton. You can ask the same question about an oxygen atom or a gold atom or a lead atom. What's going on inside? How does the picture change once I get all these protons and neutrons closely packed together? And then, of course, are we going to see any sort of signals of physics beyond the standard model? Are there things that are pictures of quarks and gluons and these existing particles? Are there things that happen at the collider that we can't explain with the picture we already have? Okay, and that leads me to my conclusions. We discussed today what's inside your coffee. For me, it's a lot of milk and sugar. I really don't like the taste of coffee, but I like coffee. But ultimately, it's all these quarks and gluons and crazy things that scientists don't even know everything about yet. But it's exciting because we're going to have this big new machine that's really going to push forward our understanding of how nature works. All right, thank you guys for listening, and I'll take it out.